you all know him, and he is in fact the one who conceived the idea about the tool, like back in deep COVID time in 2020 or 2021.
No, it's 2020.
2020, yes.
Get a lot to do.
Great.
Get a lot of time on your hands.
Having all of you having here, and then discuss about all this exciting physics we've been hearing for last 3 weeks. So here's Andy. Today he's talking about high temperature something.
Order.
Order.
Is it? I mean, is this? It should be visible, right? Okay. Okay. Yeah. So yeah. So I think this topic sort of won the Slack poll by popular demand. I have to say it was also my preference. So even if it didn't win, I probably still would have done it. But you know, yeah. So it's the last week of the school. I hope this will be sort of kind of whimsical and fun. I'll be talking essentially about statistical mechanics of systems that order at very high temperature. So yeah, probably most of today will just be a kind of review of hopefully ideas that you're sort of somewhat familiar with, but I'll try to make a little bit more explicit. I think the first thing we should understand is sort of why typical systems are ordered at low temperatures rather than high temperatures. And if we understand that really well, then we can maybe try to sort of flip the phase diagram and get order at high temperatures. So, okay, to sort of get started, right? So typically in statistical physics, we expect that if we sort of have a phase diagram, which here I will just take to be kind of one-dimensional, like I can heat my system up, and typically we find something that looks like this. At high temperatures, we see something kind of featureless, like a gas, which would be disordered. And then at low temperature, if we're lucky, we might see some kind of thermal phase transition at some critical temperature Tc, below which we have an ordered phase. And an example that you could have in mind here is I have a bucket full of water. If this is 273 degrees Kelvin, above that temperature, I have a liquid in the bucket. And below that temperature, right, the water would freeze and form solid ice. And the solid is a phase that spontaneously breaks the continuous translation symmetry of the liquid. And so for this lecture, I'll be thinking about order as essentially the spontaneous breaking of some global symmetry. Okay. And this is sort of usually the way that nature works, right? The ordered phase is at low temperature and the disordered phase is at high temperature. Okay. You might sort of say that that's a bit unfortunate that this is the way that nature works out, because usually the ordered phase is sort of more interesting than the disordered phase. I wouldn't have been able to conceive of the idea for this school if everyone is just talking about different featureless systems with slightly different microscopic Hamiltonians, right? So the whole zoo of phases that we love in condensed matter physics, density waves and superconductors, all of these things, have some kind of order that characterizes them. And even from a societal perspective, of course, we wouldn't have had the information technology revolution without magnetism at room temperature. Maybe I'm too old and, I still remember going to school and having floppy disks and stuff like this, but, we really are relying on the fact that we can have order at room temperature for much of technology and of course for life as well. So we're not all like blobs of goo. Now, okay. With that said, there are many phases that we would like to realize at room temperature, but we don't know how, like superconductivity. If we're being honest, we haven't realized that yet. It might be nice if we could sort of understand why. Are there some fundamental obstructions to realizing order at high temperature, or is it just a lack of imagination? Okay. Now, the other sort of comment I want to make before I get started with the lecture, I'll sort of review as we go. There's a very long history of trying to sort of flip this diagram so that the ordered phase is at high temperature and the disordered phase is at low temperature. I think this is because, physicists like to be kind of annoying. And so if you're told in class that this is the way that nature works, you try to find some counterexample to it to show off. So that's sort of what we'll be doing. Yes, I'm not, it is actually how I started this project. Yeah, so yes, okay. Anyway, so with that said, let's get started. So as I mentioned, I think, oh, yes. Yeah, so as I'll discuss a bit later, there are many examples of systems that sort of flip this order. So this idea has been sort of discovered many times. I'm actually not sure if all of the communities were aware of the other, but so there's the Pomeranchuk effect in liquid helium. There are certain crystals that were known to chemists, like these Rochelle salts, that are more ordered at an intermediate temperature than at low temperature. There are sort of soft matter realizations of this. Eventually I'd like to sort of give you what I hope is a sort of unifying picture for all of these systems. And the sort of concrete goal that I'll eventually try to stress is that I would like for this phase diagram to look exactly the same as this, but just to flip the ordered and the disordered phase. So I want the order to sort of persist forever. No matter how hot the system gets, it stays ordered. And that has been much harder to realize, but I'll explain how that can be done as well. Okay. All right, good. So to understand like why this is sort of the way that nature usually works, let's talk about sort of simple example. So let's take just the two-dimensional classical Ising model. So I have some square lattice, right? I have sort of spins at all of the vertices of the lattice. And each spin is either +1 or -1. And the Hamiltonian for my Ising model is just the sum over all adjacent pairs of Sx times Sy. Okay. All right. And as you know, the thermal state, you can really think of it as sort of a probability distribution on sort of a configuration space, like the set of all possible 2 to the n different spin configurations. The probability of seeing any one of those spin configurations at some finite temperature T is given by the Gibbs ensemble. So there's a normalization factor called the partition function, and then we have e to the minus beta h of s, where beta is just, of course, the inverse temperature, 1 over T. Okay. All right. Okay. Now, in the Ising model, we have a sort of Z2 symmetry, right? Which just takes a spin configuration S and takes it to -S. It just flips all of the spins. And in this sort of classical stat-mech framework, that symmetry is manifest like this. Okay. And it's this symmetry that we say is sort of spontaneously broken. So sort of formally, what does this mean if I have a broken symmetry? I'm too lazy to prepare a clicker question, but so there's no game show learning today. But if someone wants to speak up, how would I diagnose? Yeah, although quantumly, right, I could consider a superposition of all up and all down, which is symmetric. So we have to be a little bit careful about that. What? Yeah, okay, in the back. Sure. Okay. So there are a few sort of good suggestions. I think the last two are sort of similar. So we could imagine kind of looking at typical configurations and asking whether most of them have sort of spins up or down. Maybe a more physical way of doing this is to turn on an external field and see if the sort of typical configurations abruptly all have the sign of the field we turned on. But okay, let me try to give you sort of a number of different perspectives that you might take on this symmetry breaking, and then we'll see what happens. Okay. All right. Good. Before doing something fancy, let's sort of review 19th century physics first. So one perspective that we could take is purely that at the thermodynamic level, a system tries to minimize its free energy. Okay. And if we just stare at this formula, then it seems like if we're at low temperature, then we should minimize F by sort of focusing first on minimizing E. Okay. And if we want to minimize E, then we should have a ferromagnet. So in the ferromagnet, we have, is this sort of too low or is it okay? Okay, I saw a thumbs up from the other side. So, okay. So at low temperature, right, we want all the spins to be aligned. These are the sort of lowest energy states of that Hamiltonian. Okay. Now, on the other hand, of course, if we're at high temperature, so T is large, then instead we're trying to maximize the entropy and, being a bit sloppy because we'll try to be more precise shortly. At high temperature, we're trying to maximize entropy. Entropy is, of course, roughly like the logarithm of however many accessible configurations we have. And so we should just try to access all of them. So if we just consider the kind of random ensemble over all the possible spin configurations, this is definitely a featureless sort of ensemble. And, half the spins typically would point up, half of them point down, finite size fluctuations here. Okay, so here we have, right, the paramagnet, which doesn't break Z2. And of course, over here we have the ordered phase without this symmetry. Okay, so hopefully that's sort of very familiar. Okay. Now let's do something a little bit more sophisticated. So that's a sort of intuitive argument that, if S is supposed to be big, then we make S big by just having something featureless and disordered. That sort of seems to suggest that order should always disappear at high temperature. But that's sort of not a mathematically precise statement, as we'll see. So what's the sort of better way that we could diagnose long-range order? Spontaneous symmetry breaking. So the second thing we could do is we could look for long-range order in the ensemble. So if I look at, let's say, a spin correlation like the average value of Sx, Sy, here this average, right, is taken over the thermal ensemble in the usual way. I want that the following kind of connected correlation function does not vanish at large distances. Okay. This is a slightly more precise diagnostic for order. And let me sort of make a sort of brief caveat that we'll return to shortly. So here, when I write down this formula, actually this second term just strictly vanishes, right? The ensemble has a Z2 symmetry. So that second term has to vanish. So sometimes in physics, we sort of take this convention where when we talk about the ordered phase, we kind of implicitly first turn on this symmetry breaking field, sort of kick us into, let's say, a space of configurations where all the spins, or many of them, point up, and then we evaluate this average. Here, I'm not doing this. I'll return to that perspective in a few minutes. Okay, but this is sort of another simple diagnostic for symmetry breaking. Okay. All right.
Having the wrong clustering doesn't mean that there is symmetry, but the need can be unsymmetry at all.
Yes. Yeah, so I guess, but what's your point? Oh, well, in this case it does because this, yes. Well, but okay, what I would say is that, okay, so let me make two remarks. The first is that one can actually prove that this is impossible at high temperature and under somewhat mild assumptions. So in this respect, it's sort of a useful diagnostic because we'll be able to explain why in a broad class of models this can't happen. Secondly, okay, it's true that here we sort of have this implicit assumption that, like, if S contained a component that looked like the identity operator, then just looking at this two-point function would not detect anything interesting. So it is indeed true that here we're using the fact that our symmetry sort of has a nice local action on observables. And so charged observables under that local action, like spins that flip sign, sort of detect the emergence of this long-range order. Okay, the third thing, this is maybe closer to what you were getting at. This is actually sort of my preferred way to think about the problem of order in this system is that we can think of the ordered phase as a kind of measure condensation in our Gibbs ensemble. Okay. So what do I mean by this? So here, if I try to kind of give you an artist's rendition of the hypercube, of n dimensions. So each corner of this hypercube is a sort of, a spin microstate where whatever corner I'm in tells me which spins are pointing up and which spins are pointing down. But I can't draw in n dimensions, so we're going to draw it this way. So let me put sort of the state where all the spins are +1 in one corner, and the state where all the spins are -1 is in the other corner. And okay, I'll draw this figure twice for good measure. Okay. All right. So what happens is if we look at this problem at low temperatures, so what we find is that sort of with overwhelming probability, and again, this is kind of the artist rendition, we're likely to be found sort of close to one of these two corners. So most of the spins either point up or most of the spins point down. Okay. And the probability that we're found sort of in each of these two clusters is sort of approximately 1/2. Okay. And then separating these two clusters, we have the states where 50% of the spins are up and 50% are down. And these are very unlikely to be found. Okay. So the probability of being found in this bottleneck region, if you will, between the two sectors is exponentially small. This can actually be proven. Okay. A here is some like order 1 constant that depends on beta. Okay. And of course, what does our Z2 symmetry do? It just sort of flips us across the hypercube. So the Z2 symmetry takes a state in here to a state in here. That's why we would say in this case that we have spontaneous symmetry breaking. Okay. All right. By the way, so returning to the physics convention, so oftentimes people sort of implicitly restrict the average to just one of these clusters. In one of the clusters, of course, Sx can get an expectation value. Some jargon that you may find useful is that we might call one of these clusters a replica of this system. And okay. Just one other comment one can make. So without sort of knowing any details, as long as, let's say, we were sort of trying to sample this thermal state at low temperature with some kind of local spin flip dynamics, the fact that this bottleneck is very unlikely to be found in the Gibbs ensemble sort of guarantees that the dynamics would get trapped. If you started here, you'll sort of be stuck in this replica for a time that's exponential in the system size. Yeah. Yeah, so for continuous symmetry, you would have like I guess a ring. Well, what, power law? You're saying correlation functions? Yes, but yes. So when you have a continuous symmetry, this picture that the dynamics is exponentially long in system size, that doesn't happen because you have Goldstone modes. So yeah, so the dynamics is not sort of quite so slow. But there is, I think, sort of still, there's a very similar picture to this. Actually, mathematically, it might be slightly subtle to define, but yeah. Okay. All right. So that's what happens at low temperature. Okay. So at high temperature, and this is what I'll want to sort of be a little bit more explicit or careful about in a little bit. At high temperature, this picture sort of looks very different. And again, in the sort of artist rendition, what happens at high temperature is that you kind of only have one big cluster, so to speak. Again, it may be misleading because at infinite temperature, this Gibbs state is kind of uniform on the hypercube. But you could roughly think that most of the states on this cube are far from the corners. And so overwhelmingly, you're likely to be found far from the corners. Okay. So we have kind of one big cluster where we're almost surely going to be found. And the symmetry sort of maps one point in this cluster to another point in the same connected cluster. There's no bottleneck separating them. Okay. And I think this is sort of the clearest way to think about this kind of phase transition. Yes. Not really. I mean, what's happening is basically, so you could pick some sort of threshold, like I want the probability to be found in this region to be, like I pick some number A, and then I just say, like A is 0.01, and then I could just sort of pick, a region where I have very crudely, you could say, let me take all the spin configurations with a net magnetization, which is sufficiently small. And when the probability of finding magnetization in that window is sort of this small or less, I sort of put those states in the bottleneck. It's carefully, one does it slightly differently and looks instead for configurations that have a sort of system size spanning domain wall. But yeah, it's be sort of it. So yeah, as long as you're sort of right. So at a fixed temperature, if you restrict to one replica, there's a sort of typical magnetization that you see. And as long as your threshold is sort of smaller than that in absolute value, it sort of won't really matter where you choose the cutoff. Yeah. Okay. Yeah. So just as a sort of broader educational remark, so in this cartoon, right, we have this measured condensation onto just two replicas, one for each symmetry sector. But there are systems where some of these replicas are not related to other replicas by any symmetry, and you might call these spin glasses. And so this phenomenon called replica symmetry breaking in the literature, it's kind of, it's very mysterious, I think, the way that the people thought about this in the 80s, but at least to me. But the sort of very transparent picture, in my view, is that what people call replica symmetry breaking is nothing but this transition. So, okay. And one point I'd like to stress is that for this Ising model, okay, let me go back over here and make sort of one more brief remark. So in this Ising model, one way that thermodynamically we could detect the presence of order is that we could, let's say, we could detect TC at least by a non-analyticity in the free energy. And so you might think that sort of all of these definitions are in some sense the same. But this is not true. It's possible to actually have this measure condensation without anything interesting happening in the free energy. Yeah.
Or do you also go to it if you have both?
So I guess what do you mean by like having multiple Gibbs states? So I could consider dynamics, for example, that just like explicitly cut the configuration space into two pieces that can't be connected, and then certainly I have like multiple equilibria. I think the mathematical problem I'm interested in, if you like, is that I consider some irreducible chain. So basically there's a unique steady state, which is given by this Gibbs ensemble. And I want to characterize, the resulting phase. So I'm not sure if there's something else besides measure condensation. Sure. Okay. I guess. So my definition is that, so here I'm just saying, like, I think to draw this picture, the way I'm doing it here, you have to take a finite, you could take a large system, but it should be finite. Yes, I don't want to sort of worry about taking the limit in the other order, but yes. Frank? I think this is, yes, so this is related because of this property. So yes. Yeah. Yeah, so in a finite system size, right, there's a unique steady state, but there's a sort of, if you think about the dynamics that relaxes to that steady state, there's one sort of mode that has an exponentially long lifetime, and that's the mode that kind of mixes you between the two replicas. Yes. So the definition is that, so, okay, if we can take a sort of, a family of L by L grids, and we want that on a grid with a fixed value of L, there's some, in this case, there's a function e to the minus AL such that, this probability measure has this sort of clustering property with this bound. Yeah, so in this picture, yes, so here I'm only talking in this cartoon for the Ising model about discrete symmetries. Yes.
Was what you were saying about replica symmetry breaking, that even in the absence of any glass physics, the conventional ordering phase also replica.
If you want, you can call it, but I guess my point is, so in a spin glass, you can just think of replicas as, so each replica kind of corresponds to one of these clusters in the configuration space, and they may not all be related by a symmetry. But nevertheless, the point I want to make is you still sort of have this picture for sort of the onset of order. And I would say it's sort of better detected dynamically rather than maybe the kind of undergrad way of looking for phase transitions in the free energy. That's sort of an aside, but I think it's sort of... Okay. All right. Okay. So, right. So now the question, maybe building off of this example, the question that I would like to ask is sort of, is the high temperature phase sort of always disordered? Okay. So, all right. We sort of drew a similar picture already, but let me sort of again motivate this question as follows. So this time I'm going to sort of be a little more sophisticated and draw a two-dimensional phase diagram where I have temperature and some other parameter. Maybe here we think about, we're talking about some quantum system. Maybe we have a phase transition at 0 temperature where over here I have a disordered phase. This could be, for example, the transverse field Ising model from this morning. Over here I have an ordered phase. And we could ask, what does this phase diagram look like at finite temperature? And okay, in the case of the 1D Ising model, the order sort of immediately goes away, but okay. More generally, we might sort of hope for a picture that looks something like this, where we still have some sort of phase transition at finite temperature, even if we're not sort of exactly at this critical point. And, so some of my collaborators are high energy physicists, and, their motivation for studying this problem of high temperature order is that if I sort of look at this part of the phase diagram here, I might hope that that this sort of shaded region in yellow can be described by some sort of like continuous field theory. There might be some universal description of what's going on here that's not so sensitive to lattice details. Okay. So, for example, I might have, in this Ising transition, for example, there's a famous description of this in terms of the conformal field theory, okay, close to this transition. So we might ask whether that, if we could make this line bend the other way, or just like switch the color of the phases, if we have, let's say, disorder over here and order over here, that seems to suggest that there would exist some kind of continuous theory that actually breaks a symmetry at high temperature rather than low temperature, right? In the continuous description, I wouldn't see like any lattice scale cutoff. So yeah, so this is sort of another perspective for what we would like to do. And okay. From the field theorist perspective then, I would say it probably seems like this is ridiculous, that you're never going to order at high temperature, because certainly all of the field theories that we think about usually would not have this property. And it, yeah, I think it just seems quite weird. But, well, okay, you want to?
I just want to ask about, like, there's some parameters in the field theory. So how the parameters in the field theory, let's say the canonical quadratic coefficient, sign of quadratic coefficient, depends on the microscopic temperature, is forgotten, is not there in the field theory. So you could this question kind of loses meaning.
Okay, I think depending, okay, so if you're thinking of like if you're thinking about a classical statistical field theory governing this finite temperature phase transition, I think I would agree with that statement. But okay, in this diagram, let me just put an axis label here, 0. So I have some quantum critical point that spontaneously breaks a symmetry. And I might ask, like, if this line can bend the other way, then it sort of seems as if there would exist maybe like a conformal field theory that orders at finite temperature but not at 0 temperature.
But the temperature on that axis, is that just coming in through either the minus beta h of the field theory, where h of the field theory, or is it coming in off the parameters of the field theory?
So here, this temperature is that one. So, you know, I study trace of e to the minus beta h of the microscopic theory, and I ask in the continuum, is there a field theory description of this that orders not at 0 temperature but at non-zero temperature? That's sort of quite mysterious from a field theorist perspective. Okay. All right. So, okay, with all of that said, right, so now, right, so, but there are systems that are known that do, that at least, you know, in some region of the phase diagram, there are systems where the phase looks, or the diagram looks more complicated. So again, let me put my axes here. So, okay, there exist systems. I'll ramble some of them off again in a minute. There are systems where this diagram might look something like this. So again, here I have the disordered part of the phase diagram, and here I have order. Okay. So now let me imagine in this diagram, let's sort of start at like this value of the coupling and heat the system up. So if we do this, right, then we first sort of cross this line, and we actually go from a disordered phase into an ordered phase. And then, of course, at higher temperature, we go back into the disordered phase. So, you know, there are examples of this that I'll mention again in a moment. But, you know, if I stare at this diagram, maybe, again, in the same spirit as here, if this is some kind of microscopic quantum theory, I might ask, what's happening here? Like, if I focus on this critical point at 0 temperature and I heat the system up, it seems like maybe there ought to be some kind of continuous description that actually orders at finite temperature rather than 0 temperature. There are physical realizations of phase diagrams that have this shape, but it's been very mysterious. Like, is there a field theory that could possibly describe, let's say, that point? Or is this phenomenon somehow like very intrinsically a lattice effect, and it kind of can't be realized in some universal language? So that's a sort of puzzle that we would like to address. Yeah. I think you can do this in 2 dimensions as well. You can do something like this in 2D for discrete symmetry and then in 3D for a continuous symmetry. Yeah. I mean, okay, without adding like power law interactions, I don't know how to break the Merman-Wagner theorem either way. But yeah, in 2D, if you have discrete symmetry, you could do this. I'll write down very explicit lattice models that do this later. Yeah. So I think it depends on your perspective. So in the 2D Ising model, quantum is certainly not important, but you might sort of object as Leo did that, well, okay, whatever, it's just a, temperature is just a label. But I think it's much more non-trivial if you start with a sort of, a quantum, let's say a quantum lattice model with a QCP, quantum critical point, and then you ask, is there some, if this critical point is described by some field theory, I could maybe just as well think about that field theory and talk about that field theory at finite temperature. And if the field theory is sort of a faithful description of that transition on the lattice, then the thermal properties of that field theory ought to have some resemblance to the thermal properties of the lattice model. And I think now it's sort of much more subtle. I think until like 8 months ago, we didn't have a field theory that we at least knew for sure would do something like this. So in the quantum context, this is, well, okay. In field theory, we don't know, or I'm not at least going to attempt to do this, so I'll just rely on 2, because we will be talking about simple symmetries like Z2 or U1, where I'm sort of comfortable with 2. But I think again, like it's sort of not something I've thought closely about, but I believe there are ways, you could try to sort of take the thermodynamic limit first and talk about a kind of measure condensation in quantum systems as well. But yeah, again, I'm not sort of an expert on the mathematics of that. Yeah.
Generically, you're asking about the entrant.
Yes. So there's a sort of there's many historical names for this. One of them is re-entrants. Right. But again, the question is sort of, if we have this re-entrant order, let's say above a quantum critical point, like how should we understand that?
Was it known to be uncommon? Or?
I would say that as far as I know, there's basically one family of field theories that potentially had this phenomena that were identified. And then there's like spin-offs on the common motif. But yeah, but actually only recently it was established that, but those were all sort of perturbative arguments. So at a technical level, like the field theorists were only satisfied, in the last year or so, that they actually found the field theory that does this.
Maybe another useful terminology is order from disorder.
Yeah, so okay, I was going to write those words down in a moment. I would say that to me, order by disorder is like one realization of this, but yeah, it's sort of in magnets. It's a jargon thing. I'm not sure how. Okay, sure.
One critical point for which re-entrant is a universal proposition.
Yes, that's the claim. And the claim, and I'll maybe tomorrow I'll tell you sort of what those CFTs are. And I haven't sort of thought about it in detail. I could guess how you would realize them in a lattice model, but yeah, we have a field theory that does exactly this. It's really Zohar and field theory. And so yes, this is a thing. Okay. Right. So the question is basically like, is this re-entrance just always kind of a weird quirk, or could it somehow be more more universal? Can we kind of understand the physics a bit better? Okay, with that said, let me discuss some examples of this effect. So I think people have already brought up all of these, almost all of these, at least in the audience, but just let me sort of remind you of them explicitly. As I said at the beginning, it's kind of fun to be contrary and to say that, like I heat this liquid and it becomes a solid, right? That sounds kind of shocking at first glance. So physicists have tried to do this for a long time. And in no particular order. So one example of this is the Pomeranchuk effect. This is going to be high pressure liquid helium-3. And this is one of these sort of, I don't know how rare. To me, it seems slightly rare occurrences in solid state physics where someone predicted something well before it was observed in experiment. At least as far as I know the history of things. So it was predicted in the 1950s. What basically happens is that we start off in a liquid ground state. Just think of helium-3, it's a Fermi liquid. Then, okay, at some ridiculous pressure, at some very tiny temperature, I think in our paper we say it's 10 to the minus 7, but someone else grabbed that number. So, okay. So at this temperature, liquid helium freezes into a solid. So we're spontaneously breaking the translation symmetry. And then, okay, the phase diagram continues. And of course, at much higher temperatures, like room temperature, we just have a gas. Okay, so the phase diagram kind of looks like this, right? There's some intermediate order, and then both at low and high temperatures, we see disorder. That's an experimental, this has been experimentally realized. It's not just a theoretical prediction. So there's a compound called the Rochelle salt, or maybe a family of compounds. I'm not good with jargon, but it's some nasty chemical formula, and it's a crystal. And let's just say, kind of schematically, we go from having a big point group at low temperature, then at some intermediate temperature, which is around 200 Kelvin, we get a small point group, and then again, you melt the system and it becomes a gas eventually, okay, or plasma, okay. So again, we sort of have this re-entrant kind of transient order at intermediate temperatures. And something that I actually am not sure if it's realized in experiments, maybe someone in the audience knows, but this is Leo's order by disorder, which I have to confess, I really don't like this name because it's very unclear what disorder it's referring to here, in my opinion. But this is sort of, there are many lattice models of magnetism that exhibit a similar phenomenon. Yeah.
Example, Langer invoking here is, essentially going past like the upper cutoff of your typical energy theory and just like saying, okay, my molecules fall apart or something? Or is this transition also going something that's going to be seen in the effect of your theory?
Well, so I would expect that, okay, so first of all, maybe in both of these examples, these are thermal transitions, so they don't quite fit into this paradigm here. So in this sense, maybe they're not the perfect examples. But yes, I would say that, let's say if we realize this transition at 0 temperature, then I would expect that in the quantum field theory for that transition, I would expect that it orders at all temperature. Yeah. Since I don't have an explicit example of this, I don't know if that's actually what would happen. One might also worry that the effective field theory may not be UV complete. And in that sense, it doesn't really make sense to ask whether the order persists to infinite temperature. But what we have are now like conformal field theories. So they are UV complete that order at finite temperature. Okay. All right. So, good. Okay. So, in all of these examples, right, we may notice there's something that they have in common, which is that, so like all of these eventually order at high T. And I think that somehow my sense, and maybe this is like a very unfair characterization of the literature, but you know, since I'm the one lecturing, I get to do it, I guess. But my sense is that in each case, like it's a bit of a quirk of the specific microscopic physics that this is possible. And maybe, yeah. So these things always sort of have this intermediate re-entrant order, but it goes away. And so what? Oh, eventually disorder. Yes, thank you. Yes, that's awkward. Yes, all eventually disorder at high T. So the question we'd like to ask to sort of be even more contrarian is to find sort of a model in the continuum or on the lattice, I don't care, that really orders as T goes to infinity. Yeah. So I can tell you theories that have topological order at arbitrarily high temperature. They're a bit silly, but they exist. I can tell you them a bit later after I explain the physics. But generalized symmetries I am not considering because I think I was wondering if someone would ask this question. I was asked it a few months ago and I sort of had anyway, I thought about it a bit and I think there's a sort of good argument why you don't want to consider, let's say, like one form symmetries in this story, but I don't remember it off the top of my head. But anyway, I think that you can have order at high temperature in this setting, but maybe it's not for, it's almost for tautological reasons if I remember correctly. So here, let's say for this lecture, we're just talking about like global symmetries, so zero form. Yeah. Okay. All right. So let me now sort of tell you a bit of the history here. So, you know, mathematicians tackled this question 50 years ago, and they said that at least with somewhat mild assumptions, the answer is no. Okay. All right. So we have to sort of understand, right, their results a little bit before we can try to find order at high temperature. So let's do that. And I'll try to sort of at least sketch out some of this formalism. So apologies if this is a bit annoying, but sometimes it's fun to do math. Okay. So in math, the setup that they considered is as follows. So we have some state space or configuration space, whatever you want to call it. Let me just say it's some set omega, right, which is the set of all of the microstates in the system. So in our Ising model, right, this was like plus or minus 1 to the n. Okay. All right. And for the moment, let me just assume this is discrete. Okay. Just to make things a little bit easier. But that's not sort of essential. Okay. Then, right. So to specify the Gibbs state, I give you a Hamiltonian or an energy function. So for each microstate, I tell you what its energy is. And right. So basically for each of the states in this space, its probability is just 1 over z, right, e to the minus beta h, where z is the usual partition function. Okay. And okay, let me try to squeeze this in here. So so under these assumptions, there's a theorem which goes back to, I think, 1972. A guy named de Bruijn. And he says that basically if this set omega, for now, let me just say if it's finite. So here I'm imagining, here again, I'm imagining I sort of have a finite size system, but it could be arbitrarily large. Yeah. Maybe to be a little more precise, could say this. Secondly, if basically there are no hard constraints in the configuration space, so like all possible spin configurations are allowed. I don't restrict to like only spin configurations where one spin, you know, in any region can be up. Okay. No, it's different because I could have power law interactions in, I mean, yeah, I could have interactions on a general graph. This is basically saying like, it's not a hardcore lattice gas, for example. Yeah. And third, if I have, let me just to avoid being, yeah, okay. If anyone wants me to spell this out a little more, I could, but let's just say if we also have an extensive Hamiltonian, so like each spin flip can only change the energy by order 1. Okay. So under these assumptions, then for the inverse temperature beta below some critical value, and this critical value is order 1. It doesn't depend on system size. Then you can say that there's no long range order or measure condensation. Okay. And so the way I define things over here, like I don't need to specify what symmetry I'm talking about, et cetera. Just I give you any observable, I look at that, you know, connected 2-point function, and I get that it goes to 0. Yes. Yeah, so you could take, you know, x minus y is of order L. Or, you know, yeah.
We're doing a family of systems.
Yeah, so you can, it's, yeah.
And BSS doesn't depend on this.
Yes. Yeah, so there's one beta C for which, you know, any choice of lattice in that family, for the same value beta C, it obeys this property. And the points, you know, x minus y can be, it's really a stronger condition. Actually, let me say this condition, to put it in a way that makes sense. So this connected 2-point function will be bounded by, you know, there's some other constant, but it looks like this. So actually you have exponential decay in the distance between the 2 points.
Anyway, I mean, that the second, the SX and XY are 0 in any point.
Yes, that's fine. That's what I wanted. Because those are charged under symmetry. So those under my semantics, those always vanish. So, but you don't even have to talk about a symmetry here. You could just say, like, I give you any observable. And the reason we're doing this is just to say, if I give you the identity, then that doesn't count. But I give you any observable. I don't need to talk about a symmetry. There's no sense in which the system can order over long scale. There can be any long range correlations of any kind, unrelated to symmetries or related to symmetries. Yeah. So here, to talk about the distance between x minus y, so here you need some notion of, this is kind of, if you will, it's like the graph distance for whatever the interactions are in H. So like if I could give you like a Hamiltonian that has nearest neighbor interactions on some expander graph. And then x minus y is just the distance on that graph between two vertices.
This thing has nothing to say about that.
So, okay, I don't know off the I'm sure that someone has generalized it to that case, and this is probably like 1/100 minus epsilon or something, but you know, yeah. No. But here, let me just define it this way. So in your example, this bound becomes trivial because everything is connected. Okay. All right. So all right. Let me just say sort of a few words about why this is the case. You know, this might be a sort of forgotten part of the literature, but okay. So why can't we have any kind of long range correlations? Well, okay. Again, here I'm going to be sort of a bit sloppy, but I'll at least try to give you the idea of why we should expect this theorem to hold. So remember that this is the calculation we're trying to do. And okay. You know, if beta goes to 0, we could always try to just Taylor expand this exponential. So we could say like 1 minus beta h and so on. Okay. And okay, you know, formally this is a bit sus, right? Because h is extensive. So this series, it does converge, but you need to go to very high order. But okay, here's where I'm going to kind of elide the details. You can imagine sort of the following. So here's my point x, here's my point y. Let's sort of consider some terms that we might have to deal with in this sum. So if we look, for example, at the term that's like beta h to the power 4, right? We're bringing down 4 terms from the Hamiltonian. Maybe those terms are somewhere like this. So we might have 1, 2, 3, 4. Okay. This term shows up in this sum. And so what we notice is that, so term 1 here is sort of canceled by this denominator. Terms 2, 3, and 4 all kind of play with spins x and y, so they're a little more non-trivial. However, this specific configuration here also contributes to the disconnected average, right? So there's no way that I could sort of tell apart the contribution from this yellow configuration if I was looking at the connected or the disconnected average. Okay. So the only things that can contribute in a non-trivial way to my connected correlator are the kind of clusters that span all the way from x to y. So this sort of red kind of chained configuration contributes to the connected correlator. All right. And now here's where we use our extensivity condition, because again, here being a bit heuristic, but read a book if you want to know all the details. Because of this extensivity, at high enough temperature, sort of no matter what change we do to a single spin, kind of the contribution from each one of these terms is small. Okay. And there are at most, let's say, n factorial of these clusters if I'm on a graph with finite degree, which I'll assume for simplicity. And we have an n factorial here. It could potentially undo the factorial in that series, but this is still small. So this series will converge. Okay. And again, this is sort of a physics argument, but or physics version of the sketch, but this is basically why we'll never have order or long range correlators at high temperature. Okay, so that was known for classical systems for a very long time. And there's a sort of version of that that was also known in quantum systems for a long time, but this has become a sort of revitalized subject in quantum information and computer science recently, because one might ask, is the task, yeah. Oh, so think of the delta H here as like the contribution. So some of the clusters, like this one in yellow, don't contribute to this disconnected correlator. So think of the delta H as roughly like the terms that can contribute to this connected correlator kind of at each order can contribute sort of at most something much smaller than T at high temperature. Again, I'm not going to try to be too precise, but just trying to give some intuition. Yeah. Yes, like if, in the Ising model, for example, this delta H would be 4J or maybe 8J. Example. Yeah. Yes. So this goes by the name of cluster expansion. Yeah. Okay. So right. So the same thing happens in quantum systems, but actually in some sense there's something stronger, which was shown recently. So as I was mentioning, sort of the information theorists got interested in this question because one task you might want to do on a quantum computer is to prepare like a Gibbs state at some finite temperature beta. And the question is like, is that a non-trivial task for a quantum computer at any temperature? And so under sort of similar assumptions to the ones that I wrote over there, the answer is no. Okay. So yeah, okay. So let's say I prepare what you might call the quantum Gibbs state. This is going to be the density matrix e to the minus beta h over the partition function. Okay. And right. So what is known is that sort of all the same words as before. For sufficiently small beta, we have two things. So there's no long range order in correlation functions. So trace of rho AB, etc. So that's also true. But there's also something interesting, which is that this was a huge surprise, at least to me. There is zero entanglement in the following sense. So the density matrix can be written as a sum over product states. So Frank was talking about product states this morning, right? As like very simple states that you can store on your classical computer. And the high temperature Gibbs state of all quantum systems is just a sum of products, a classical sum of product states. Okay. So in this sense, there's zero entanglement that's not classical. or zero entanglement entropy that's actually coming from entanglement and not just this classical mixture of product states.
Does that mean that, connected correlation should be 0?
No, because for example, like take H to be a classical model like the Ising model, right? So you could still potentially have this condition, but have classical correlations that are long range. So you can use the same cluster expansion to say there's no long range order, and then you use actually I think there's sort of similar techniques, but you can do this much stronger statement and argue that there's zero entanglement. So these are extremely strong statements, and they tell us, right, if we have any model of interacting qubits, we're certainly not going to have any kind of high temperature topological order. So any kind of uniquely quantum phase from this perspective seems like it should be restricted to extremely low or low temperature. All right, any questions? On n qubits. Yeah, so it's like, A1 alpha. Yeah. I'm pretty sure that they have a constructive. I mean, it may not be the most efficient, but yeah, I believe it's constructive. It's been a while since I looked at that paper, but yeah. Okay. All right. So it's Yuan Tang. She's not the first author because it's alphabetical, but she's on that paper. Yeah.
Just going, you have to find out this is the context of the carrying state on computer, but then you need to purify it probably, and then you still get some single data. What is it not the
I guess so the reason that one cares about this from the kind of quantum advantage perspective is that this is not something that's difficult to simulate on a classical computer. So if I have an algorithm to find these psi A's, I can just sample this distribution very efficiently. So the idea is like there's no point in sort of using a quantum computer to prepare this state because there's nothing you can learn. Oh, sorry. Yes, that's my bad. Yeah, I meant that like there's no point to make this state because there's nothing interesting in it. Yeah. Okay. Yeah. What do I call what?
Is there some version of quantum case also like for the classic case is the second condition, which is no hard constraint. So it's the same for.
So I thought about this for a while. I mean, there was a literature at some point, at least it was popular like 10 years ago on quantum models that had like exact constraints on the Hilbert space. So like in the context of maybe these like PXP type models, you could imagine like a spin chain, but you just throw away any state that has like two ones next to each other from the Hilbert space. Mathematically, I mean, you could define a Hilbert space that has that structure, but it's kind of a weird thing in the sense that like, I don't know how to define entanglement entropy anymore, because how do I trace out, some degrees of freedom when they're sort of locked to other, like when I trace out some states in the Hilbert space, the sort of density matrices I see don't necessarily have the same constraints, or there's, I think it's a bit tricky.
Simple number of particles you have to work in one Coulomb some of the lost particle number factory.
It's
probably what Coulomb some with fixed number of electrons.
I think it could be a fixed number of particles. So what I mean are models where like you might allow particle number to fluctuate, but like two particles can't be within a certain distance of each other. That violates an assumption in this theorem, and actually you can have high temperature order but yeah. But quantumly, it's a bit funny because yeah, as I said, I don't know how to make sense of certain notions of entanglement, et cetera. Like the notion of a product state is not defined anymore to me in an obvious way. So anyway, okay. All right. So it seems like the mathematicians say that everything is sort of disordered at high temperature, and that's kind of disappointing because, as I mentioned at the beginning, like ordered phases are more interesting than disordered phases. We would like to, of course, realize complicated ordered phases in a noisy environment at room temperature. We could make a lot of money if we had a room temperature superconductor. So, okay. All right, so I'll probably just like set up the discussion and then we can finish it tomorrow. But let me try to sort of recap what we would like to do. So our goal is basically to take, we'd like to find some kind of model. For example, maybe we have a quantum theory where there's some kind of critical point, and I want the phase diagram to look like this. So I want to have an ordered phase, a disordered phase, and then when I heat this system up, I can start from the disordered phase, I sort of transition into the ordered phase, and then I order forever. I never go back. Yes? That's right. Yeah. So indeed, I mean, if the theorem had something to say about field theory, then we wouldn't have written a paper, or at least it would have been entirely wrong. So yes, so indeed, the theorems don't apply directly to field theories, but still, I think it's a bit subtle, right? How are we going to beat this theorem? Because it seems like reasonable lattice regularizations may well obey these assumptions. So it's you could do it that way, but I think that's not what I'm going to do. I'm going to make them countably infinite, and it's not unphysical, right? We have bosons in nature, but that's sort of the trick. Okay. So, but right. So we would like to create this, and okay. So, all right. So if this is our goal, let me remind you. I guess I still have them written up here. So let me just go over here. Right. So we had these three assumptions. Obviously, we have to break at least one of them, either classically or quantumly. But let's start classically. I would say that 2 and 3, I sort of don't want to break. Okay. So I want to keep these. Okay. Because it sort of seems like if I lose these, maybe I'm like not really doing physics anymore. For example, I could give you a configuration space that only consists of all the states in the Ising model that have magnetization, between -1 and -1/2 and 1/2 and 1. And this model, you could say, orders at any temperature, but it's for a trivial reason, right? So you might worry, and people could find a sort of slightly more non-trivial example that orders, but basically to avoid that kind of objection, I want to keep both of these two. This one's potentially a little subtle once we break the first one, but at least like morally, I would like to say that at any finite temperature, H is only changing by a finite amount almost surely when I change one of the sites. So this one, let's try to relax. Okay. And right, the reason that I think that one is sort of okay is that we know that bosons, so bosons have a sort of countably infinite state space. right? If I give you one boson, I can have 0 bosons, I can have 1, I can have 2, and this goes on forever, okay? And why do I like the fact that this goes on forever? Well, one kind of heuristic way you can think about the cluster expansion is it's sort of an expansion around the uniform Gibbs measure. We're saying that in some sense, like the distribution that we're sampling from is sort of locally very close to a uniform measure. But there is no uniform measure on this state space, okay? So that's sort of why we might think that this is, in some sense, the most intriguing way to try and avoid our theorem. And I should say that I think it's fun to be motivated by some math problem of trying to beat this old theorem. But even if anyway, I think that if we can beat the theorem, maybe the lessons that we learn will guide us in designing practical models. Maybe the order won't exist to infinite temperature, but maybe we still have some like general tricks for boosting the temperature of order in models that we care about. So, all right. Let's sort of ask how we could use bosons to break these theorems. And all right, maybe I can at least sort of get started explaining this model in the last 8 minutes or so. Okay. Okay. So let me again sort of, I have a 2D square lattice. I have now, instead of a spin on every site, I have a boson, if you will, just a degree of freedom, right, that takes values in this set. And my Hamiltonian is just going to be the following. Yes, for good measure, I'll put some constant here, u. Okay. This is a very gimmicky model, but we believe in some sort of ongoing work that you can also take away these 2s. It's just a bit more of an involved analysis. But we believe that at least for some parameters, the same conclusions hold. Okay. So maybe the first thing I should check is just that this model is actually, okay, maybe in the interest of time, I'll just sort of tell you what happens, and then tomorrow I can sort of go through a little more carefully. So, okay. Right. So let's guess what the phase diagram of this model looks like. So, as we did with the 2D Ising model, we could sort of start with 0 temperature. So at 0 temperature, it's easy. So this model actually has a unique ground state. Which is all n equals 0, okay? In the sort of fancy modern jargon, this is a frustration-free problem. Okay, very simple. So the ground state has no particles anywhere, and that's it. Now let's think about high temperature. So, okay. Yeah. At high temperature, it's maybe slightly trickier, but slightly asymmetric lattice. But at high temperature, what's going to happen is that in typical configurations, we find the particles will sort of form these checkerboard configurations. Okay. And the number of particles on every other lattice site will scale with temperature. And if we try to put a particle on the opposite checkerboard, right, we pay an enormous energy cost right away. So certainly if I form the checkerboard, I'm not going to want to change it. And right. What I'll argue a little more next time is that in this model, actually, if you sort of think a little bit more carefully, you can convince yourself that not only is it sort of hard to put particles on the other checkerboard locally here, but actually this configuration plus the one shifted by one lattice site dominate the Gibbs ensemble system. Yeah. So suppose that U is infinite, so I just don't allow for two particles to be on adjacent sites. Then this Hamiltonian, it violates this assumption, so we don't like that. But if we just take that limit for a moment, that term's gone. So the Hamiltonian is just like a sum of independent oscillators, if you will. We can evaluate the partition function exactly by just doing the geometric sum. And you find that on each site you have sort of order T particles. It's of course strongly fluctuating, but that's the typical value. Yeah. We did that because it makes the argument that I'll sketch tomorrow much simpler. But we now find that you can also use linear interactions, which is probably more relevant for experiments. But linear interactions also work, but in that case, there's a critical value of this parameter U above which you order at high temperature. Yeah. Yes. Okay. So this is a system that orders at high temperature rather than low temperature. We might conjecture that the phase diagram of this model looks something like this, let's say at a fixed value of U. So we would say that, we have this disordered, often this is called a lattice gas at low temperature. So at low temperature, most sites are empty, but occasionally you just find a site with one, maybe very rarely two particles on it. And then, at some critical temperature, you form what I'll call the lattice solid. And the lattice solid, right, spontaneously breaks Z2 symmetry. So there's a sort of discrete Z2 translation symmetry, which is spontaneously broken. Yes.
Here, that TC is bigger than 0.
I have not argued that for you, but it is bigger than 0. Yeah. Certainly, at least numerically, we have. It's without a doubt bigger than 0. Intuitively, why it's bigger than 0 is because what this model looks like at low temperature is that so at low temperature, like having two particles is pretty energetically costly. So I can always make the density of doubly occupied sites as small as I want if I'm arbitrarily close to 0. And then when I'm arbitrarily close, and then sort of, this is a physics argument, right? But in this limit, this now looks like a sort of usual hardcore lattice gas, but with the wrong sign in the fugacity. And we know that the lattice gas would order, that's sort of one heuristic argument for this. But so we conjectured and sort of numerically verified that this is actually the sort of 2D Ising universality class. So this is sort of a known, in this sense, this finite temperature phase transition is described by a known universality class, but we've just swapped the ordered and the disordered phase. No, U is finite. That's right. It stays ordered forever. I'll explain this more at the beginning of the lecture tomorrow. But yes, this is the simplest realization of a model that orders at arbitrarily high temperature. Yes. So it depends on what kinds of perturbations you add. In some sense, the answer is no. And I would say the general answer is no. And the reason for that is as follows. So if you're interested in low temperature stability in StatMech, in the field theorist language, you're asking basically how many relevant perturbations are there. Usually there's one, but usually it's some finite number. You just count for them and you tune this finite number of knobs, and then this is robust. Here, at high temperature, I'm asking about stability against irrelevant perturbations. And there's infinitely many of them I could add to this Hamiltonian that destroy the phase diagram. Right. From the field theorist perspective, you could maybe say that like the field theory in some sense doesn't exist if you turn on those irrelevant perturbations, and so they don't care. In that sense, this is completely stable. All relevant perturbations kind of don't destroy the conclusion of high temperature order, as far as we can tell. Yeah. In the usual one. So something that's irrelevant as you kind of flow the RG to lower energy scales, those irrelevant perturbations can destroy this kind of high temperature order. Let me give you a simple example. Yes. So yeah, but I think it's sort of still true that irrelevant. Okay. So okay, I see the confusion, I think. Okay. Yeah. Let me just put it like this. Maybe it's so if we go to this Hamiltonian, this perturbation destroys long-range order at high temperature. And you might think that this sort of feels like it ought to be irrelevant from a low temperature sense, right? If epsilon is small, this doesn't seem that bad, but it completely changes the physics at high temperature. There's infinitely many powers I could put there. I could put 6, 7, 8, etc. So in that sense, these models are extremely finely tuned.
Infinitely many relevant.
Yes, in this sense.
So would there be an intermediate phase?
Yeah, there would be an intermediate phase still.
There's a second transition rate order.
Yeah, so if you turn on that epsilon, then you disorder again at high temperature. And there's some window, I think in this case, TC, there would be like a TC prime, which is epsilon to minus some power, above which you again disorder. Yeah, I think the point of this example is just to sort of, as we'll see, get some like very concrete examples of like the physical mechanism that enables you to make TC as high as you want, if you will. The TC, let's say, governed by that epsilon. And then once we know that, we can kind of hook up all kinds of field theories that order at high temperature, et cetera. And build models of high temperature superconductors. So, yeah.
Does this like works in arbitrary domain?
Yes, except for one. Yeah, so we don't know how to beat the Merman-Wagner theorem or whatever the discrete version of Merman-Wagner is, probably someone who's dead. Sorry, but you know. Pyrals, sure. I think he won't be offended. So yeah. Anyway, so yeah, we can't order in 1D, but we can order in 2D. And for continuous symmetries, it would be something similar. Like you could get a BKT, like a bound vortex phase at arbitrarily high temperature, but not a superfluid. Yeah. Sorry, you mean in this problem? What's the order at low temperature? So as I'll discuss, yeah, if you have order at high temperature, it's necessarily driven by entropy. There's no way around it. So yeah, that's.
Here, like the low temperature order and symmetry is different from high temperature.
This is true. Yeah, I mean, as long as you had order. I mean, we also have models where there's just no TC at all, and you just order it at any temperature. That's also possible. But I think it's kind of more fun to sort of just show that the transition flips. But we can also make order that just never goes away. Yes. But and the physics is kind of the same in both cases of the high temperature. Yeah. Mm-hmm. Okay, sure. Let me sure. So let me just write it out. So each term here, H only acts on the degrees of freedom in subset A. This is an arbitrary, that's a decomposition I can do. And so this means like all the subsets A that contain a specific vertex, which I'm calling I. Let me just sort of write it this way. You know, in some units, you could put another number here if you wanted, but basically, no matter what you do to a single bit, like maybe you can subtract off the minimum value if you want to be pedantic, but basically changing one bit can only change the energy by an order 1. Yeah. Anything larger than 2. Including 2 with this, but okay. Actually, at 2, what's going to happen is you'll have to go to a sufficiently large value of epsilon, and then you destabilize it. But 2 plus delta in the exponent would destabilize it for any epsilon. Yeah. Yeah.
About the number of sites, it seems like you might get this check and forth pattern even at 0 time. Does this like weakly breaking of condition 2 makes it so that the thermal fluctuations destroy the order at high temperature, or in this case would we have check and forth pattern?
I would say that, I mean, so if you work in a fixed, if you work in a fixed number ensemble, then it's, yes, then it's true that at all temperatures you see, well, sorry, there will be a temperature which scales in some way with n, above which you disorder if you only have a fixed number of particles. So here the point is that in the configuration space, think of the bosons as more like spins, like there's some bath they can jump in or out of. So it's not a conserved, like sum of bosons isn't conserved too. Of course, this is an equilibrium problem. I haven't specified the dynamics at all, but yeah, I'm just asking questions about the Gibbs state of this H as written. Yes. So we call this entropic order. I'll kind of explain that name tomorrow. It's the same mechanism as this, but this I think is a model that will illustrate it more clearly, in my opinion. Yeah, so you can have first order transitions or continuous transitions of this kind. Yeah. Yeah, you wouldn't have a sort of QFT description of the transition. Yeah. Here the classical field theory description of the transition is known. It's the 2D Ising CFT. But yeah, there are also like quantum mechanical models that one can write down that also behave kind of similarly, where they'll have zero magnetization at 0 temperature and finite magnetization at finite, and non-zero magnetization at non-zero temperature. Yeah. In the back. Yeah. Yeah, so this is with the, because here, so with the finite dimensional Hilbert space, it's sort of easy to define extensive in this way. Here, okay, what I would say about this Hamiltonian is like, it's not extensive by this definition. That's sort of an important, okay, maybe I should I'll put a sort of quotes around this. What I would say is that morally what this Hamiltonian does is that it's a sum of terms which, they're polynomials with finite coefficients. So for any fixed number n, like in the thermal ensemble, almost surely any move that you make, let's say in a Gibbs sampler, will change the energy by a finite amount. So but it does break the cluster expansion because delta H could scale with temperature, for example. And that's of course possible because we have infinity. So it's still true that in some sense, the way that you beat this condition kind of critically relies on having an accountably infinite state space. So I would still say that like breaking the first one is the crucial part.
Let's take a couple more questions after thinking Andy was now.